So today we are going to discuss about the dislocation arrays and pileups and how it is going to influence the mechanical properties or strength of a particular material. That we are going to learn today. So first, you should know that dislocation move out from the source, and that can be Frank-Reed source, under the action of an applied stress, and up to which time now until the dislocation are held up at barriers. So it looks like a scenario. If you look at it, the slide, that is a Frank-Reed source. We know what is Frank-Reed source and how dislocation multiplication going to occur there. Those things are clear. So from a source, suppose the example of Frank-Reed source, any source dislocation will move out and it goes, and by the action of any kind of external applied force or stress or load, and up till that time it will go when dislocation are face the obstacles, or it is going to held up by barriers. So when it will held up at the barriers, what will happen? The pile up barrier ever in, then you have to understand what are the different barriers can be possible. One is very commonly known, that is grain boundary, and other dislocation. Some dislocation are not movable or glissile. So sessile dislocation can be a barrier, or sometimes precipitate can be a barrier. Maybe if the precipitate size is very small, and that ultrafine precipitate can be a barrier. So if you see in the picture that from the Frank-Reed source, dislocation are going to produce. So we can tell that a Frank-Reed source keeps produce dislocation loops until the frontier dislocation loop is stopped at a particular barrier, a strong barrier. Now let's see what does mean. So already I told, when there is a dislocation, it goes out of that source and move out by the action of applied stress, and it goes up till that time when it up till that scenario when the dislocation are going to held up by the barriers or obstacles. And very commonly known barriers are grain boundaries, sessile dislocation, and if you are not asking question, please mute yourself. Okay. So now we are going to understand the next scenario, that how different kind of dislocation moves out from the source and reaches to a particular barrier, and how they are going to pile up. And in this slide, we are going to know that things by a schematic diagram. So if you look at the symbol upper head T or lower head T, actually they are representing edge and screw bolts dislocation. Okay, so now S in the slide is representing the source. So suppose the slip plane is Y plane, and you can imagine that suppose the barrier is there parallel to the Z axis, and then let's the dislocation mix type, suppose B and at theta to the dislocation Berger vector, B at theta to the dislocation line. Now what is the scenario? If you look at this slide, then you can easily understand that dislocation 1 lies on the Z axis, and let dislocation nth dislocation is at the head of the pile-up, and let L be the pile-up length. Now what will happen when one dislocation reaches to the barrier, then next dislocation will come and it is going to pile up just next to the previous dislocation. That way dislocation are going to pile up. Now if we can resolve the Berger vector into BE and BS as denoted in the slide, that subscript E, capital E, equal to B sine theta, and B subscript S is the B cos theta. So same Barchan vector for all dislocation as they are from the same source. So dislocation are coming from same source. So the Barchan vector will be the same. Now you can assume that barrier has short range stress field so that it interacts with a nth dislocation. And when you are taking that assumption, then you can rightly go for subsequent consideration. Therefore, every dislocation in the pile-up except nth1 feels three forces. What are those forces? The one is applied tau star, that is the difference between applied shear stress and internal stress. Then interaction of edge component, interaction of screw component. It's very obvious. And that actually leads to a scenario, the piling up. And when that piling up is occurred, then again you can want to move the dislocation out of that obstacle or barrier, then you need more stresses. And in this slide, it's just the introduction that how the pictorial representation, schematic form, that how dislocation pile up near the grain boundary. And we'll understand that more detail in the subsequent slide. So first, we are talking about dislocation pile-up. But why we are bothering about the dislocation pile-up? What is the significance of dislocation pile-up? The significance is that already I told one thing. You may understand that dislocation, when you are putting a dislocation and that reaches to a particular obstacle and stays there, then it actually hinders after the dislocation, when further dislocation when is moving towards the obstacles. So in this way, the pile-up actually increase the stress or applied stress required to move a dislocation across the pile-up region. So you can tell that stress ahead of a pile-up is proportional to the number of dislocation in that pile-up. So you can understand that pile-up is a significant phenomena because it actually directly can be related to the strength of a material, yield strength or strength of a material. How strain hardening concept can be understood based on the dislocation pile-up phenomena. So again, I am repeating, stress ahead of a pile-up is proportional to the number of dislocation present in the pile-up region. So hence, the applied stress is magnified by n as it acts as a barrier. So it can be very, very large. So if you take an example where grain boundaries are there, act as a strong barrier, then what will happen? Stress concentration may nucleate dislocation in the next plane, and one of the mechanism to explain the Hall-Petch relationship based plasticity. Hall-Petch relationship, I think everybody knows about that. Or create a crack at the boundary, which may propagate along the grain boundary, leading to a final failure of the material. This is often in case of ceramic, which are the brittle material. Okay, so what is actually happening with the pile-up phenomena? How it is related to the strength as well as certain failure behavior of certain materials. So if you look at that pile-up region, that stress for the pile-up may fracture of the grain boundary. And I told that it can be a basis for Hall-Petch relationship. What is Hall-Petch relationship? Everybody knows that sigma equal to sigma A, or tau equal to tau A, multiply by ky d to the power minus half. Here, d is the plane diameter. So it actually tells you as a statement, or what it actually tells you, what reveals, what is revealed by the Hall-Page relationship. It is revealing that if you go for finer grain size, the strength will be enhanced. So if you look at the dislocation pileup, so when dislocation pileup will be there, then movement of this new dislocation will be hindered. So if there is a number of grain, the volume fraction of grain bond is more in a particular matrix, then more you can tell the more pileup, more chances of pileup of dislocation will occur. Why? Now dislocations are going to be piled up due to the presence of obstacles like grain boundary. So if you increase the grain boundary volume fraction or amount of grain boundary, you are actually enhancing the possibility of pileup of dislocation, and that in turn enhancing the stress required to deform the material. So that's why that can be directly related to the strength of a material and yield strength of a material, and that actually represented by Hall-Page relationship. And another thing I told that one thing is Hall-Page relationship can be explained using dislocation pileup understanding. Another thing I told that it can create a crack at the boundary like certain brittle material like ceramics, and which can propagate along the grain boundary, leading to a final failure. So what that does mean? So first you have to understand that suppose shear stress due to pileup may cause fracture of grain boundaries or nucleate slip activity in the neighboring grains. How to explain that? Now, if there is a lot of dislocation are present, and we know dislocation is a line defect, and dislocation is so a defective region will generate, and that may create a scenarios that micro crack or initiation of fracture may occur because there is a lot of stress concentration around the pile of dislocation, because a lot of dislocation are piled up. And if it reaches to a critical value for a brittle material like ceramic and other things, there is a strong chance of having the fracture. So we can tell that, again I am repeating, the pileup stress, shear stress related due to pileup may cause fracture of the grain boundaries or nucleate sudden slip activity like what I told regarding the explanation of Hall-Page relationship. So today's very short lecture. Thank you, but nobody asked question. Nobody stopped me.
Yes, sir, because everything is going smooth and we have understood.